Okay, so today we are going to be investigating polarization a bit more, and in a similar thread, we have something called charge by induction. So we'll talk about that a bit today. Then we're going to start getting more mathematical here. I'm going to introduce Coulomb's law, and we're going to play around with that for a bit. All right, now polarization, as we discussed in the previous class, was something that we said is going to occur on a neutral object. By putting something that's charged in the presence of a neutral object, it's going to change the state of the object to some extent. And we want to investigate how that's going to happen. We also have made a distinction between conductors and insulators, and polarization happens a little bit differently in those two types of objects. In this example here, we have something, it's called an electroscope. So this is a metallic object. It is a conductor. We bring a glass rod that has been rubbed with silk, and now we know that imparts positive charge to the rod here. Now, for the purposes of what we're talking about here, it doesn't matter if this is positive or if it's negative. The effects are the same. But when we bring this rod close to the sphere, we see that the leaves, now these are like these hang-in metal plates, and normally they hang straight down, but when you bring the rod close to the sphere on top, we see that these leaves, we call them, they expand out. And what that means is they're experiencing a repulsion, okay? And so we're going to look at what's happening there. So this here, we're talking about our metal. We have our conductor here. And by bringing the positive rod close, what we are doing is we are inducing a macroscopic separation of charge, okay? I say macroscopic because on either sides of the object, we could talk about a surface charge density that exists on either sides. And that, that's something that would exist across, not across the whole metal, but I mean, it's not continuous. In between these two areas, there's no charge floating around there. It exists on the surface. But the negative charge gets attracted to the positive rod, and then as a result of the attraction of the negative charge, a positive charge will build on the other side. What's really happening here is there is a slight shift to sort of what we call the sea of electrons that exists inside of a conductor. But the macro effect is that negative charge builds up on one side and positive charge will build up on the other side because there's a deficit, basically. And it kind of ripples its way through the metal, and the overall net effect is this charge separation. Now, that's something you should always be thinking about when we say polarization. Those things are synonymous. Charge polarization and separation of charge. That's ultimately what's happening when things get polarized. In the example of the electroscope, when we bring the positive rod and we put it in close proximity, or in proximity, I should say, close proximity. You can say close proximity. I just said it. I don't think it's really a phrase that, whatever. Anyway, when you bring it in, maybe you can't. I don't know. I'm not thinking about, I shouldn't be thinking about this. All right, anyway. The negative charge builds up on the top, and then, of course, positive charge builds up on the bottom, but because the leaves are free to move, they experience a repulsion between them, which gives you an indication of, well, it gives you an indication of a few things. It's a way to sort of qualitatively determine how much charge is on the rod there. Because if we were to, say, more vigorously rub that rod and therefore increase the amount of charge on there, we would actually see the leaves of the electroscope open up even more. Okay. Now, this object that's here, though, this electroscope, okay, assuming it's been grounded before we start everything off, and when I say grounded, you remove any excess charge on it, it has a net charge of 0. There's just a separation of charge that occurs. So, that's that. And then I don't know, I think I'm going to get into charge induction today. But charge induction would be like this. Say I were to take this setup here, and I take like a samurai sword, you know, those real sharp ones, those nice sharp ones, and I just slice this thing in half. Well, you separated charge, and when you slice this in half, you've kind of permanently created that separation of charge, and now this rod up, this sphere up here, will be overall negative. It will no longer be a neutral object, and same thing with the things down here, and that's something we call charge by induction. I'm not sure if I'm getting to that today or ever or what, but it just popped in my head. I think I'm going to get into it today, though. I don't know. All right. This is showing a microscopic view of what's happening here, and this is one really common setup that we're going to be doing several times in the class. It's a very simple application of these principles here, and that's what's called the electric dipole. Okay. Now, when we talk, for you chemistry lovers out there, when we talk about objects being polar, like the water molecule being polar, there is an inherent electric dipole that is established across the molecule. And what that means is there is a separation of charge. The way that the bonds are shared between the hydrogen and oxygen atoms creates an excess amount of positive charge on one side and a negative charge on the other side, and that's all just a function of how greedy the nuclei are, you know. So those well, whatever. A neutral atom will have a roughly uniformly distributed electron cloud. And if you've ever seen the orbital levels in these things, those more advanced probability distributions, you see that they're symmetric. And that ensures that, for the most part, things stay neutral. If your plans are in one day to take 211, that's one of the last things we do in that course, is we dig into the hydrogen atom from a quantum mechanical standpoint, and we work out some of the basics of how those orbital levels look. It's pretty fun, to be honest. Mathematically, it's a complete nightmare. I mean, you should see the math behind it. It's part of me doesn't even want to show it to you because I envy some of the innocence of individuals that have not seen some of the equations involved. Yeah, anyway. All right. It's a scary... Well, if you really want to know, wait till 211. What that? Oh, Richard had 211. Yeah, well, the stuff we do in 211 is not too bad. Just and you get off the hook because you don't have that kind of level of mathematics. But what happens is when you have to solve, I don't want to. I'm not going to get into this because I'll just go on and on and on. But we didn't get to it because you have to do those things in spherical coordinates, and you have to do all these crazy. I don't know. I'm not. I guess I want to talk about it, but I'm not going to talk about it. Anyway, so electric dipole. So when a atom, whether it's naturally polar or not, is in the presence of an electric field, okay. Yeah, 3D is cool. Well, okay. I gotta control myself here. All right. So whether you have a molecule that's polar or not, in the presence of an electric field, meaning you're just in the presence of other charges, like we see right here, there will be a slight shift in that distribution. You're completely changing the nature of this atom here. And then the atom becomes polarized. And that is what we refer to as an electric dipole. And like I said, it can happen from polarization. It could also come about naturally, depending on how the bonds are between the atoms in the molecule. All right. So when you look at an insulator, that's what's happening. When you go look into an insulator, the charges aren't free to move like they do in the conductor. And so what happens is the atoms experience this micro polarization inside them. And what ends up happening here is if you look, say, right about, here, well, everything's electrically neutral there, right? And if you look right here, everything's electrically neutral here. The issue comes when you have the far left side with a bunch of negative charge built up and the far right side having a bunch of positive charge built up. There is a difference between the conductor, though. Okay, charge is not free to move. Charge just experiences a very small micro separation. Whereas in the conductor, things move. So what you find is that conductors, because of that motion, are much better at having charge flow through them and do a much better job of creating a strong polarization effect. Okay, so anyway. Ooh, it's some good tea, people. Wish we had taste-o-vision in here. You can taste this tea. Actually, I don't want you to taste my tea. That's kind of weird. Never mind. But it's good tea. A little tension tamer. A little green tea mix. All right. Question for you. Metal spheres 1 and 2 are touching. They're both initially neutral. All right. And we got an order of events here. The charged rod is brought near. The charged rod is then removed. The spheres are separated. What are the charge states of the metal spheres? Yeah. So think about that for 30 seconds. Letter in the chat. Let me know what you think. Like that smash button, right? As those kids say. All right. Let's see what we got here. Ooh. B's and D's and B's and D's and this little A going on in there. Little A going on in there. No C. Oh, no C. Well, we don't like C. Don't put C in there, though. I'm warning you, don't put C in there. All right, so I guess what we have here is we don't know if we are neutral or if we've become charged. All right, the answer is D. D, because guess what happens? Here's the order of events here. Actually, I don't want to tell you what the order of events are here. Yes! Oh, I heard like a voice, and I'm going insane. And it was just Alexa. Not to rule anything out about me being insane, but... All right. Before I explain that last one, let me ask you another question here. We're going to do a similar thing, but we're going to mix it up a little bit now. We're going to bring the charge rod near, and then we're switching the last two events around now. The spheres are separated, then the charge rod is removed. What's going to happen there? So in the last question, we stayed neutral. What's happening here now? So again, letter in the chat. Let me know what you think. All right, let's delve in here and see what we got. Oh my goodness, a lot of B's. A lot of B's. I think we're learning something. Or you're just a lot of lucky guessers. All right, the answer is B. Okay, so what happened in the previous example was charge polarization occurred. But then you remove the rod and everything goes back. The Things go back really quickly, by the way. We're talking like a nanosecond. It's fast. Here, we bring the rod in contact, we have the polarization that occurs, then we separate the charges. That's what I was talking about, the charge by induction. I guess I am talking about that today. No samurai sword needed for this one. We just separate the balls, and now we've created charge states on them. Overall, the two balls are electrically neutral, but individually they're not. There's a negative charge built up on number 1, and number 2 is a positive charge built up. Great. Fantastic. Okay. So you need the charge present. And as far as you're concerned, the separation of charge is instantaneous. The little micro shift in the motion of charges is so quick. It's, like I said, nanoseconds. So anyway. All right, another question for you here. This one's good. This actually relates to a homework question. I think it's your homework that's due on Wednesday. This is very similar to that. Let's see here. Anyway, we're going to touch P and Q together. And then we're going to touch Q and R together. And we want to figure out what's going on with R. So the concept here, if it's not clear, is that if there is a separation of charge, they try to neutralize as best as possible. Okay, if you were to put, for example, if I were to take the metal sphere and touch it with charge, that charge ends up on the sphere, but what it attempts to do, it attempts to spread out as much as possible. And if there's any excess charge that's on it to begin with, there's going to be an attempt to neutralize things. So that's what you got to keep in mind here. So let me know what you think here. The sky looks less yellowish today. So I think that fire is calming down. What percent containment we got here on this fire? $62, huh? That's pretty good. 62% containment. All right. Nice to know. Nice to know. All right. Let's see what we have to say here. Overwhelmingly C. I'm liking C quite a bit. It is C. Now, what's happening here? Here's what happens. When you look at P and Q, and you touch them, there's an excess amount of positive charge. So the positive charge is going to want to distribute itself evenly over both spheres as soon as they touch. That means P will acquire a 1 nanocoulomb charge, and Q will acquire a 1 nanocoulomb charge, positive. Then we separate them. They keep the 1 nanocoulomb charges. Then Q and R touch together. The net charge between Q and R is 0. So when the charges, when the spheres are touched, they neutralize completely, and they both have a charge of 0. Do note that if you were to add up the charge on all three, we get a positive 1 nanocoulomb. And guess what? When we're done touching things here, we end up with a positive 1 nanocoulomb charge overall as well. So, can't destroy charge, can't create charge, unless you're God, but God doesn't really do that because he doesn't want to mess up the world.
Dr. McKevin?
Yes.
Could you repeat that again? How you still got 0 nanocoulombs?
Yeah. So the first step here is you add, easiest way to do this is add the numbers up algebraically, right? So a plus 4 minus 2 is an overall plus 2, and then we divide that by 2 because we have two objects, so we get a 1 and a 1. So the next state here after you touch this stuff here, if you can do this, is just to say, you know, after you do the first step, you can say, you know, this is plus 1 now. This is plus 1 now. And that's what happens when we touch these things. And then this one is, of course, stays initially at -1. But then now when we touch Q and R together, and when you add up these two, all right, that's a 0. And so 0 divided by 2 is still 0. And so touching these two after you did the first step will neutralize everything. So you'll end up with a 1 on P, and a 0 here, and a 0 there. Okay. Yeah, if something is, if I'm saying something's 0 nanocoulombs, it's a neutral thing now. It can still experience polarizations and things like that, but there's no excess charge on it. By the way, this question, just to be clear, had nothing to do with polarization at all. Okay. All right. Let us move on then to the next slide. Which probably has some more physics on it. I hope so. Really? Coulomb's law already? Okay. So let's put some math behind this now. Putting some mathematics behind what we're doing here. So when you have, now we're dealing with point charges first. Okay, we did a lot of qualitative things previously. And that involved some single charges, some bulk amount of charge, some surface charges. And we're going to start with the easiest stuff and work our way up. And the easiest stuff is the point charge. So in the example here, we have two positive charges. They have magnitudes Q1 and 2Q respectively. Something in coulombs, right? And they will experience a repulsive force. Now, according to Newton's third law, they are going to both experience a repulsive force, okay? Same magnitude, opposite direction. The amount of force that is experienced by these charges is inversely related to the square of their distances. Inversely related. Well, it should remind you of gravity for a couple reasons. One, because it is an inverse square law, like gravity is. But unlike gravity, we are going to prove in the next chapter why we have an inverse square law. It's a function of being in three-dimensional space, and that since force weakens with distance, the further you go away from a charge, you can imagine a sphere that surrounds the charge, and the surface area of that sphere goes as an R² factor. That's involved. But anyway, we'll actually prove why this is the equation for force. It's kind of neat. It's kind of neat, actually. There is a proportionality constant here, like there are with many forces. And it's 8.99 times 10 to the 9th newtons meters squared over coulomb squared. Okay? So what, you put in things in meters, you put things in coulombs, and this spits out a force that's in newtons. Okay? So a couple things to be mindful of here. One, there are absolute values on the Q's. Okay? And there's a reason for that. As you might remember from Physics 110, you generally don't want to work with negative signs. Because negative signs almost always are responsible for the direction of vectors. And what I'm showing you right now is simply the scalar version of Coulomb's law. This is not the complete law. It's missing the vector notation on it. Okay, notice my F's don't have vector notation on them. So this is simply the magnitude of the force. And the direction is a little tricky to do. Not too tricky, but a little tricky. But I'll explain that in a minute here. Okay? So, move on. If we have two negative charges, same thing, right? Nothing is different at all in the magnitude of their forces. There will be things different, typically, though, here, in that one common thing that we do is we have protons as our positive charges, and we have electrons as our negative charges. And so if a proton and electron are experiencing an attractive force between them, they're going to experience pretty different accelerations. Okay, forces are the same, but their accelerations are dramatically different because there's a huge mass difference The proton is something like a little more than 1,000 times more mass than the electron. I think it's like 1,047 or something crazy like that. I can't remember off the top of my head what it is, but it's something wild. 1.67 divided by 9.11. Really? 1,833? Okay, I was a little off there. All right. The proton's about 1,833 times more mass. All right. I thought it was closer to 1,000, but it's not. Okay. The positive negative charges will experience an attractive force. The magnitude of the force is the same. The direction is simply different. That's it. Okay. Oops. All right. So now, here's what's tricky about. I'll say a little bit about the vectors now. Let's say I didn't have my charges at a weird angle here, right? If you're just doing things on the x-axis, then it's very easy to attach your vector notation. Because, you know, for example, if I were to tilt this system so it becomes horizontal, right, I would say that Q1 has an I hat charge and Q2 has a negative I hat charge, right? That's why you don't really want to throw in the negative signs into your Q's here. And again, do not do that. When you use Coulomb's law, don't stick in a negative sign anywhere. You will, but don't. My advice to you is to not do it. Because negative signs need to be manually put in depending on what the direction of the force is. Okay? A negative charge doesn't produce a negative force. No, it doesn't. A negative charge can produce a force that points to the right or the left, and so can a positive charge. So be careful about that. We'll do some stuff with that soon. All right. What is this here? I said all this. That constant K, we are going to use it for a little bit. One thing that's a little annoying about this stuff is that we have kind of like two different constants we use. There's this K, and in place of K, we can use 1 over 4 pi epsilon naught, where epsilon naught is a completely different constant. The issue with that is that the K here is just, again, it reminds us a lot of gravity, right? And so in that way, it's nice to have just a single number there. But ultimately, when we really dig deep down into this stuff, we see that there's another constant in this epsilon naught that has a relationship to K, and that becomes more valuable. And so at some point, just out of nowhere, I'm just going to switch it up. And that will probably be next chapter. So you'll stop seeing K's, and you'll see this 1 over 4 pi epsilon naught business. But I guess I'll warn you before we actually do that. All right. Fantastic question here. Two uniformly charged spheres are firmly fastened to and electrically insulated from frictionless pucks on an air table. So basically, what we're saying here is we got these two spheres, they're charged, and they can kind of freely move back and forth without any friction or anything going on. The charge on sphere 2 is 3 times the charge on sphere 1. Which force diagram correctly shows the magnitude and direction of the electrostatic forces? So I'm going to give you a good minute to think about this one because there's a lot of information here. Woo! A lot of 5s. Ooh, got some 3s in there. All right, let's talk about it. We can talk about everything here, right? Number 1 is wrong because these are two positive charges, and they should be experiencing a repulsive force. And one appears to be repelled, another one appears to be attractive. So I don't think so. This one's out. Out. Here we go. 2. Oh, I like 2 a little bit, right? Because we are seeing repulsive forces here. What I don't like is that Newton's third law is not being obeyed here because the forces are not equal and opposite. So, wrong. 3. Wrong for the same reason. These things got to obey Newton's third law, and the forces are not equal and opposite. 4 is wrong because it's just like 1. Okay, it looks like 1 and 4 are doing that Dragon Ball Z fusion business. We don't do that here. 5. I like 5 a lot. I'm digging 5 because I see a repulsive force, and I see that the forces are equal opposite directions. So I like that. I'm going to stick this with a bunch of green check marks. That's fun, right? 6 is 6 is not. Yeah, well, 1's not doing anything here, right? So I don't know. Whoever made 6 was just desperate to come up with something here. Yeah, the little finger deal. Looks like they're about to do the finger thing, and they're about to touch. The spheres are about to touch, and they're going to fuse into some version of Coulomb's saying or something. Anyway, what's wrong with 7? None of the above. No, that's not right. Here, I have to. Actually, you know what I'll do here is for 6, I'm going to put a bunch of question marks. Like, what are you doing, number 1? Come on. You got to do something. All right, so that's what it is here. So there's a couple things to pay attention to here. Newton's third law, a lot more important than you realize. And the directions, very important here. Now, 2 and 3. Yeah, 2 and 3 are very close to each other in how they look. Let me clear everything out here, though. The difference between 2 and 3, obviously, is that 2 experiences the larger force, and in 3, 1 experiences the larger force. But nobody should experience a larger force. They should be experiencing the exact same force. 2 and 5, well, here's the difference between 2 and 5. In number 5, the right sphere has a vector that's much shorter than in 1 and 2. And we have to obey Newton's third law here, so we have to have equal and opposite forces. That's being obeyed number 5, not obeyed number 2. The one thing about 5 that we don't care about is the actual length of the vectors. They have to be the same, but they could be any length we want to, really. They're not. Without any other interaction in this situation here, we have nothing really to compare them to. So if we just compare them to themselves, they can be as small or as large as we like. So anyway, let's do it. No, stop with the question marks. Okay. The charge of sphere 2 is twice of that of sphere 1. Which vector below shows the force of 2 on 1? So, which vector am I going to throw in here? It's Monday. Forgot it's Monday. I was wondering why everything was just dark and dreary and depressing. And then I realized it's because it's Monday. Not good. But every Monday ends, though. So that's a good thing, too. I'm looking forward to this. Bees? Bees? No, people. Not B. What? Not B. I'm just kidding. It's B. I'm just kidding. This question was, hey, do you remember what we just talked about 1 minute ago? Okay. I did this for a reason. Because I find this happens a lot in the class. People really mess up Newton's third law of these problems. So I'm trying to really drive it home to you, right? Okay. The charge of sphere 2 is twice that of sphere 1. Which vector below shows the force of 1 on 2 if the distance between the spheres is reduced? Reduced to r over 2. So what we're going to do is we're going to move them closer together, right, by a factor of 2. And which one of these vector lines is going to be the right one? I can't believe I didn't make that assignment. Ugh, okay. All right, see what you got to say. I tried to trick you. Didn't work. It worked in some of you. It is D. Oh, that made me feel nice. This Monday got a little better. Yeah. Inverse square law. If you reduce the distance by a factor of 2, you're going to increase the force by a factor of 4. And we don't have a vector on here that's 4 times as large as the original vector. It's not C. I could understand C, but it's just not the right amount of increase. It is an increase. So you got half of it right. But it's got to increase proportionally. Okay, A is weaker. That doesn't cut it. B's like nothing ever changed. So good, a little more than half of you, I think, got that. So that was nice. Okay, fantastic. A lot of questions today. A lot of questions. A lot of concept here. A lot of concept. The direction of the force on minus q. That's the lowercase q. That's the one over here. What's the direction of the force? Now, to be clear, if it's not clear, net force. Net force, I should have put net. The answer is D. See a lot of D's in this chat. Because negative lowercase q is experiencing both a repulsive and attractive force, but the negative charge is closer, so that force is a little bit bigger. This is also what we refer to as an electric dipole. There's an electric dipole here, and what can be a little tricky about it is that these two charges here, even if they're very far away, by the way, they don't necessarily add up to 0, and then you say, well, there's no charge on Q at all. The fact that one charge is a little bit closer actually matters, and we don't do this today. In fact, I think we're going to be covering this on Wednesday, but we actually can work out what the force is here, and we see that it goes as an inverse cube factor, actually, which is kind of interesting. So, and that's the nature of any dipoles. Even quadrupoles work that way to some extent. So that's interesting. Okay, let's start doing some math. Let's start getting the calculator out. Let's start crunching numbers here. We want to know what the net electric force on charge A is. Well, let me draw some stuff here. So we can see that the force from B will be attractive, and it will point to the right. And I'm going to arbitrarily draw a vector that goes that way. In fact, let me erase that. I'm going to make it a blue one for my blue electron, or green, whatever I don't know, what is that? That's blue. To me, that's blue, but I think people would tell me it's green. But anyway, I got a force that goes to the right here. Oh, cyan. Don't get all technical on me. All right. We got a force that's to the right from the negative charge. Now we got a force to the left from the other one. I'm going to draw that one orangish. Now the question is, is it going to be bigger or smaller? Well, it's farther away. True. It's twice as far away. So if it's twice as far away, the magnitude of force can be down by a factor of, remember, 4. But our charge is up by a factor of 7. So ultimately, if I'm going to draw this vector out, and I don't know exactly how much bigger I have to make it, I'm going to work out the math right here soon, but the repulsive force from charge C will be larger. Yes, it's farther away, but it has proportionally more charge on it. And so the net force will be to the left. But let's look at the math behind it, okay? Okay, so for each charge, we are going to have a magnitude of kq1, q2 over r squared. have a free body diagram here. Probably not necessary to do a free body diagram here, but it never hurts, right? Never hurts to do it. We got our small f B on A to the right and a larger f of C on A, okay, going to that left. I like to use lowercase k, not capital K. I mean, whatever textbook I used many, many years ago where I grabbed the slide from the capital K, I don't like that, but whatever. So F net will be the summation of these two forces, and note that I'm putting things in vector notation now. The F of B on A will be a positive I hat, and I stuck my little I hat at the end there. And then for C on A, I have a negative I hat. And then note that all the charges that I put in here are positive, right? So even though there's a negative -1 coulombs here, I don't put that in there, okay? That negative charge tells me whether I have an attractive or repulsive force, and then I put in my vector notation that corresponds to what direction the force is, okay? The B on A is positive and the C on A is negative, so I have that in here. So I got my charges in here. Do note these are nanocoulombs. That is 10 to the -9. So I got 1 times 10 to the -9, 1 times 10 to the -9 here. This one's a 7 times 10 to the -9. Note that I have centimeters in this problem. And because of the proportionality constant here, you got to keep things SI, strictly SI. You got to have things in coulombs. So you got to work out your prefixes there. And you got to work out things in meters. 0.01 here, 0.02 here. Now, let me tell you something. Okay, put down the video game, wake up, whatever you're doing right now. I got a very important message for you. Okay? You got to put meters in here. Are you going to put centimeters in here? When you do your homework, when you take your tests, and when you just move on and you're now, yeah. So Eric, I'll get to your question. Are you gonna put meters in here? You're not. Should you? Yes. Are you? No. Should you? Probably. Okay, I'm just warning you. This is the #1 mistake, which maybe it should make me happy that it's the #1 mistake in a way, because it's not a conceptual thing. It's just like, can't remember to do it. Okay, now why do we give you centimeters like for every single problem? Why would we just give you meters? Well, I don't know, but it's not that hard to manage this stuff, you know? Anyway, meters. Okay, meters. In fact, I think what I'm probably gonna do, and I probably can't do this because it's mean, I should create like a wall of shame on my webpage. Every time you do something like that, I'll be like, look what they did. And everybody's gonna be like, it's not that big of a deal, McGovern, really. And I'm like, okay, well maybe it is, but I don't know. Okay, my advice to you is to not put centimeters in these problems because it doesn't work, right? All right, Eric says, can we use 9 times 10 to the 9? Maybe. It's a sig fig issue here, right? So in this problem here, we got 2 sig figs on everything. So can you get away with 9.0? Yeah, you can do that. If you have a greater number of sig figs, you should do the 8.99. So just, if you have 2 sig figs in the whole problem, you can get away with 9.0. That's okay. That's perfectly fine. Anyway, do math, as one does. And we multiply all this stuff out, do the subtraction. We end up with a net force of negative 1.6 times 10 to the -4 I hat. So the force is to the left, and it's in newtons. Now, do note something here. You know what? This is what I'll do. For the end of the semester, if you don't make a single centimeter error, then I might give you a compliment, okay? I don't even give my kids compliments, so that's a big deal. Put it that way. All right. Or just have a shirt that says use centimeters. I don't know why that sounds funny to me, but yeah, just have a shirt. Don't use Use meters. It says use meters. And then when somebody asks me why you have that shirt on, and I'll say, look into my eyes and see the pain. See the pain. And if you can't understand that, then move along. All right, I haven't had much coffee. I use meters. Matthew, you're funny. Focus, people. I'm talking to myself, not to you. Charge Q is in static equilibrium. We want to know what charge 1 is. Now, if you're super savvy at this, you can probably do this in your head. Right? You can probably do this in your head. But I'm going to work it out mathematically, and then I'll explain to you how you could actually get away with doing this in your head just fine. Okay. So what's happening to Q2 here? Now, just to be clear, Q1 and the 5 nanocoulomb charge are stationary. So somehow they're locked down. They're not going to fly away. Okay. And then Q2 doesn't need to be locked down. It's just in static equilibrium. So what's going to happen in this problem here? What's going to happen is this. Q2 is going to experience a repulsive force, right, from the 5 nanocoulomb charge. And it's going to have a vector that looks like that. And then we're going to get to cyan, apparently, cyan, to the left, that is equal. Am I not screen sharing?
You are, but like I think you're still on the previous problem.
Oh, so I'm not screen sharing. Not appropriately screen sharing. And my annotations are gone now. Fantastic. Okay, sorry. It's, again, maybe I'm dumb, but Zoom's like, you're screen sharing, and I'm like, but it doesn't say what I'm screen sharing, just like, you're doing something. I'm like, okay, thanks. I'm doing something here. Never tells you what I'm doing right. And maybe there's some easy way to check that. There probably is. I'm just dumb. All right, sorry about that. All right, so these are supposed to be equal vectors. Sorry, it looked like that wasn't exactly equal. Let me shorten this one up just a bit. Maybe there, so. So now, how do we do this? Well, we're twice the distance, right? So it seems like this charge is going to have to be bigger, but by how much? Let's look at it. Let me switch to my example. All right, so I got my, it's a crude free body diagram. It's not technically a free body diagram, but I don't really need that for this one here. F net is 0, so that means the forces that are exerted on, the two forces that are exerted on Q2 will be equal to each other. So I simply got to put in my KQQ over R squared. The K's drop out. The Q2s, they appear in both. This is a static equilibrium, not because of anything it's done on its own. Okay? There's no pride that Q2 can have in being in static equilibrium other than the fact that it's a positive charge. This is strictly determined by the external factors of Q1 and the 5 nanocoulomb charge here. And so I put my 5 nanocoulomb 10 centimeters away. I got Q1 now 0.2 meters here, and I solve for Q1. And what you see here is we have, look at what's going on here. This is what I mean about doing this in your head. This turns out to be a proportion, right? It's just it's proportion. And so when I solve for Q1, you can see what's going on here. It's the magnitude of the 5 nanocoulomb charge times a factor of 4. Right? You're twice the distance. You need 4 times the amount of charge to have the same magnitude of force. That's what I said. You could just look at this and be like, oh yeah, it's got to be 20. Because if you're twice as far away, you have to have 4 times the amount of charge. Boom, that's it. Simple enough. Now, if you want to mathematically show it, which I've done here, that's how you do it. We end up with 20 nanocoulombs for a negative charge. Okay, so it's a nice thing to keep in mind. Now, can you always do that in your head? No. If the numbers are easy to work with, yeah. Like these are not too bad, right? Twice the distance, 4 times the charge, or you can go the opposite way with that. If you know that you have something that's 4 times the charge of something else, you know it has to be twice as distant as the other one, so things like that. I mean, you're never going to go wrong with just throwing the equations down. but you can speed up things a little bit if you can see these proportions here. Okay, and it's a neat thing to do. I'll put it that way. Okay. This is tricky. I'm gonna try a screen share again. This is tricky for me. I mean, not for anybody else apparently. What direction would the force take in each region if a positive test charge were placed there? Okay, let's look at it. We have effectively 3 regions here. Okay, 3 regions. So if we're now region number 1 is going to be on the left-hand side here. Okay. And if I put down a positive charge, what's going to happen? Well, it's going to be repelled by the big one and attracted by the smaller one. But we got not really a problem, but we got a nice simplification. We're always going to be closer to the bigger charge. Right? We're always going to be closer to the bigger charge. That means the negative charge will never be stronger, right? It's a smaller charge and it's farther away. And so there's no way the negative charge can dominate the interaction, right? So what you can draw here, and I will draw here. How big can I make this thing? Oh, don't do that. No. You can't make an arrow go the other way? I don't want an arrow to go the other way. Oh well. I'm gonna do this one here. This arrow, I'm gonna make it enormous. If you put a positive charge anywhere in this region, it's always gonna be repelled. It's always gonna fly to the left. Okay. Because again, there may be a little bit of attraction from this one, but it will never be greater than the positive charge here. All right. Next region to investigate. The next region to investigate is the region in between them. What's going to happen here? Well, if I put a positive charge down, it's going to be repelled by the positive charge, and it's going to be attracted by the negative charge. Well, that's great, because that's always something that will be to the right. So it doesn't matter where you put it in there, right? We're going to have motion to the right, or it's going to try to move to the right. Okay, that's my right. That's my screen. That's my right. Okay. What about over here? Now it gets a little tricky, because when we're on the other side now, now we do need to be aware. Oops, I didn't mean to do that. Now we do need to be aware of how close we are to that negative charge now, because now we're in that situation that we've been dealing with here, where we're closer to a smaller charge, and there will be some sweet spot, basically. Some sweet spot where everything's held together. Right? So where's that going to be? Well, look at the charge ratio. 4-to-1. What does that mean? That means the distance ratio is 2-to-1. Right? Because the inverse square law. So how many units away is this thing? It's 3 units away. A dash here, a dash there, a dash there. All right, that's 3, 4, 5, 6. There's a sweet spot right there. That's it. If we put the positive charge here, by the way, it doesn't have to be a positive charge, it can be a negative charge too, right? But if I put a positive charge right there, that is equilibrium. That is equilibrium. Right there. I gotta put a U in there. I can spell this, right? Oh yeah. Spelling skills are on point today, even though it's Monday. Equilibrium's right there. Now, what happens when we're on to the left of it? Well, if we're to the left, we're closer to the negative charge, and we're going to experience an attraction. So the force is going to be this way if we're in this region. If we go beyond this point, then the distance factor becomes more important and we repel. Okay, so, but this is the sweet spot right here. Okay, and again, if you're super close to the negative charge, you can experience that, right? But if you get really, really, really far away, then the small distance between them is not a big factor, right? And so you're gonna really feel it more from the positive 4 there. But that's what we're looking at here. To the left, we go to the left. In the middle, we go to the right. We have a sweet spot right at that position because, again, charge ratio of 4 to 1, distance ratio is 2 to 1. Okay, if we're on the left of that, we're moving towards the negative. We're on the right, moving away. That's a great problem. That is a great problem. Let's hear the questions. I usually have questions about this. The equilibrium point is based on this. So, if you have, a static equilibrium situation, right? Then what do you have? You have this. You have a proportion, right? Q1, okay? Q2, right? And then we're going to divide. So I'll put a little division symbol here. Boop. Well, I didn't mean to make it that thick, but oh well. And then down here, right, we have our, and again, the Zoom whiteboard annotations. I mean, if you know, I've never figured it out. I don't think you can do subscripts, superscripts, things like that. I've never figured it out without like copying and paste it from some external source. I don't think even that works, honestly. So this is like R1 squared. Over here we got R2 squared. And it's the nature of the proportion. Okay, I know that looks sad. It was a little sad. Doesn't look like much of a ratio, does it? Let me try to move this a bit here. So we got that. Put some space between here. That's a little bit better, and then I'll draw a nicer, less thick line. So that's my proportionality here. Okay, it looks a little better. So the idea is that if I am going to put in a factor of 4 up here for the charge, how does that cancel out with something on the bottom to give me a ratio that's still 1? Okay, well, if a 4 is up top here, on the bottom you have to put in a 2. 2 squared is 4. Okay, say the charge ratio was 9 to 1. Right, 9 to 1. Take the square root of it. The distance has to be 3 to 1. Okay, it's all because of the squared factor here. Okay, if we didn't have a squared factor, it would go 1 to 1 like that. It'd be if you're 4 times more charged, it's 4 times farther away. If it's 5, it's 5. If it's 6, it's 6. But because of the squared factor, okay, if you have 100 times the charge, well, guess what? Now you got to be 10 times farther away. This is square root proportionality between them. But again, if you don't see that, perfectly fine. Then you go back and you do Coulomb's law and you do the example that we just previously did, where you equate the forces and you look. Okay, so again, let me just go back over here. What I would direct you to is this whole stuff right here. And you can see how the proportionality works, right? And these 2 steps here. So, all right, so I'm going to move on because I do need to get through the rest of these slides. I don't know how many more slides I got left. Hopefully not too many. I think I don't have too many, actually. No, I don't. Okay, great. All right. So now, I guess I'm going to show you it today. I thought I was going to show you the next chapter, but I guess I'm not. We will stick with K for a while, but as we move on and we start doing a little bit more complicated things, eventually we're going to switch that up. And instead of K, we're going to have 1 over 4 pi epsilon naught. And there's a few reasons why that is. It's because the 4 pi comes naturally out of some geometry that we're going to do, and the epsilon naught is more closely tied to the physical behavior. In fact, we're going to develop expressions later on that are super, super simple, and they only contain epsilon naught. And if we had K, then things would look really weird and messed up. So, all right. Now, when you have problems where there's multiple forces involved, which you will, I mean, you should expect that, superposition is obeyed. So if you have multiple forces that act on an object, you simply need to add up the vector quantities of all the forces and create a net force, which then you can figure out magnitude and direction. Of course, when you do things when you do superposition with vectors, you have to make sure that you match up. Every vector has to be expressed in i's and j's, right? I hat, j hats. And then you add up all the i's, you add up all the j's, you get your net vector, and then you can figure out magnitude and direction, as hopefully you remember from Physics 110. Okay, so a couple questions, and then I got one more example to do. Which of the following vectors indicates the correct direction of the net force on the charge at the lower left? So we got 3 charges here. We got a positive charge up here, to the right, up and to the right. We want to figure out what the net force is. So the combination of all these. I'm going to step away for 1 minute because the answer is B. That's right. It's B. Why? Well, there is this one up here. Let's draw some vectors in here. All right, let's do this. Let's get some vectors up in here. Here we go. That's not what I want. Let's try this one more time. Okay, let's make this a little thicker. I'm really sick of this orange, but I guess I'll keep it. C actually shows the vector from the top one, and A shows the vector from the right one. Now, what D is, the 2 charge up here is there's going to be a force that's down and to the left. Now, one thing that's a little unclear here, unfortunately, it is a little unclear, and I do apologize for one thing here, is that this distance here doesn't really look like it matches with that distance right there. It's supposed to match. It's supposed to match. So my apologies if that confused you, but my intention was the vertical distance here and the horizontal distances are the same. And so what that does is it produces a net force that's at a 45-degree angle, and the idea is that this is up at a 45-degree angle, so it just kind of reinforces the forces down here. And in fact, I mean, A and C don't have to be the right size vectors. B is the correct in terms of direction. I mean, it did say here direction, not really magnitude. Because the magnitude would probably be a lot bigger, to be honest. But I should fix that in my slide. I'll make a little note for myself in 1 year to fix that. What is this slide? Okay. Come on. Come on, Zoom. Work with me here. Which of the following vectors indicates the correct direction of the net force on the charge at the top? Okay, so we got a positive Q and a negative Q. What's happening here? Doo-doo-doo-doo-doo. D's, huh? Okay, all right. D's right. D is right because, now check this out. This is good stuff right here. Yes, a repulsive force from positive Q up and to the right. A attractive force from negative Q down and to the right. Now guess what happens here though? Again, assuming that the distances are the same, which they do look like they are right now, the vertical components of these two forces cancel each other out, and the horizontal components of the forces reinforce each other, and you get a net force that is purely to the right. And I'm going to do a problem in a minute here that shows what the magnitude is going to be. But a very important principle here is there is symmetry involved. And when you can identify symmetry in problems, it can vastly reduce the amount of work that you do. Okay? The symmetry here is that these charges are symmetric about a vertical axis here. And as a result of that, their vertical components will cancel. There will just be horizontal components here. Let's do a problem. Let's do a problem. Oh, come on, Zoom. All right. What is the net electric force on the 1 nanocoulomb charge? We got symmetry here, right? All right, we have an axis of symmetry that's vertical here. Okay, so if I want to draw out forces here, let's do that. A repulsive force is going to be up this way. We're going to have a repulsive force up this way. And as you can see, what this does is it removes any horizontal net force. So you can simply say this. You don't have to show it mathematically. I mean, you can, and you will get that at 0, but you can say, due to symmetry, horizontal components of the force cancel, and we only have vertical components, which will combine together in a net force that is purely upward. Okay, in my opinion, this is clear enough that you can simply say, by symmetry, there is no horizontal components of force. So then what will be the vertical components of force? I'm glad you asked that. Let's look at my example. All right. So the angles that are drawn here, I already showed you what the vectors look like. If I did a free body diagram, which you ought to do here, the angle that's made with the vertical axis is 30 degrees. Okay, these are 60s down here, so it's 30 up here. And my F net is this. Check it out. There's 3 things going on here. Okay, 3 things. This is good stuff. I just made your Monday way better. I know my Monday's way better now. Anyway, F net is going to be 2 times the force times a cosine 30 j hat. 2, because there's 2 components of vertical force, right? F is just the magnitude of the force. They're the same charges at the same directions. Cosine 30 is the vertical component, all right? The vertical component of the force here. I went with a cosine 30 because I decided to define my angles with respect to a vertical axis. So again, let me go over one more time. There's 2 here because there are 2 vertical components. The horizontals cancel out. There's 2 vertical components of the force. What's the vertical component of the force? It's F cosine 30. That is my Y component of the force here. I have a J hat indicating that it's up. Now I just got to throw my numbers in here. 9 times 10 to the 9. Oh, that's the K value. Okay, I got my 1 nanocoulomb in there. I got my 2 times 10 to the 9. That's also nanocoulombs here. And then centimeters. Got to put in meters. Right? And then punch all the numbers in here. Don't forget, I have cosine 30 in here. Check your calculator. Make sure you're in degree mode. It's tragic, but every now and then I get that student that takes their test, and then I start looking at their answers, and I'm like, what's going on here? And all of a sudden it hits me. They're in radian mode. And then I'm super nice, and I sit there and I work out all the problems in radians, and I try to give them the benefit of the doubt. 3.1 times 10 to the minus 4 j hat is the end up being the force. So notice these are small forces for centimeters and nanocoulombs. This is what you should expect for forces. They're rather small things here, all right? So that's it.